doing class first to get the knowledge we need for the section, and then homework. So let's start with the domain for log functions. This is still in 4.2. We are still in 4.2, domain for log functions. Okay, so let's start with, let's say, with the problem on page 490. Let's say 76 on 490. And we have f of x equals log base 5 of x plus 6. Like before with, let's say, let's go back to another function that we looked at before. We looked at f of x, and we had this example a minute ago, the square root of x plus 1. How do I find the domain of the square root first? What do I have to write? And then we'll go back to the log for a minute. What do I have to write? It's in your notes. It's in your notes in the test that I just returned. What do we write?
Square.
I cannot square for the domain. I square if I solve an equation. Yes.
It doesn't equal 1.
No. I can take the square root from 0. We just wrote it a minute ago. It's right here. It's right here. It's the same. I selected the same function. I selected the exact same thing. So what do we have to write in order to find the domain of the square root of x plus 1? Can anyone dictate? X plus 1. Excellent.
0.
Excellent. So then x is equal to -1, so the domain of this function is -1 to infinity. I just wanted to refresh your memory on this, because in the same way, same kind of type of, or if you want the same type of inequality or condition we have to state for the log function. Can anyone help? Remember we said log is a function with restrictions. It's very similar. The idea is the same pretty much. It's not the same function, but the idea is the same. I have to write that x plus 6 is greater than 0. This time in this function we cannot plug in 0. In the square root we can plug in 0, but in the log not even 0. So whatever we apply log to, and in this case we apply log to this expression. This is what is log applied to. That expression, like here, the square root is applied to this expression. Therefore, this one has to be greater than or equal to 0. In the same way, x plus 6, I cannot put the equal symbol here, however. So then x greater than -6. So the domain of this function, the log function, in this case, is -6 to infinity. So I wanted to bring these two functions together in the hope that you will remember them together and say, oh, okay, the square root and the log are kind of the same when I have to determine the domain. There is a difference, of course. They're not the same function. But there is a difference, right? But the idea is pretty similar. Is this okay? Okay, let's look at another example of the same kind. So let's say 78, same page, 78 on 490. And that function, we have f of x equals log 7 minus x. Before we determine the domain of this function, I want to add a piece of knowledge here. Of course, we have two special log functions, like we had two special exponential functions. Of course, one is common log function, and the other one is natural. Do we have any idea of how would the common log function look like? What is the expression? So they are paired. They are paired with the common exponential function. Remember, the common exponential function was f of x equals 10 to the x. What do you think the log function that is the inverse of 10 to the x, how will it look like? They all have to have log. I mean, there is no escape of that. Well, in this case, it's log x, and 10 as the base is understood. It's already assumed. So if you go back to your calculators, as we did last time, when we look at 10 to the x, here it is, 10 to the x and log are on the same key. One is activated with the second key, and the other one is just the key, right? So why are these two together? It's because they are inverses of each other. Excellent. And log, as you see, has no base. It's assumed to be 10. Like the square root. We don't write the square root of the index 2 because we know the index is there, although we don't write it. So, okay. So now here is the natural exponential function. What do you think its inverse function would be? That is a little bit more difficult to figure out. It's this key, of course, the same key, e to the x and ln. ln means natural log. Why don't we write NL? It's because it comes from German. That's the only reason. It should have been NL, natural log, but it's logarithmic natural. Okay. So coming back to when we see ln x, we really have to think in terms of the base being e. And the exponential function that is called natural exponential function, of course, is this. They have to have the same base. An exponential and a log have to have the same base if they are to be, or if they are inverses of each other. Same thing here. They have to have the same base. Otherwise, they are not inverses of each other. Okay, perfect. So now coming back to our problem. We're asked to find the domain of this function. And I'm going to ask you, I don't see the base. It doesn't matter. All logs, all base, the domain is determined in the same way. But I would like to ask you, what is the base here? I don't see a base. It's 10, and it's common log. Excellent. Great. So then what do we have to write? Remember, it's similar to the square root function. What do we have to write in order to determine the domain of this function? Can anyone dictate, and I'll write it? So this is the same example with the previous one.
So then is it 7 minus x equals 3 greater than?
Excellent. That's it. It's the same idea, same thing, everything the same. This is just the second example for you to have it. However, when we move 7 to the other side, we get this. And now we have to either multiply or divide by -1. And when we do that in the inequality, when we apply that procedure in the inequality, what do we have to do? Excellent. Thank you. From greater than to less than. In this case, the domain of this function is -7. And now I would like to look at a word problem in which we will see an application of the log function. Any base. Any questions on this problem? Any questions here, please? Any questions? Anyone? Okay, so let's look at 119 on page 491. It's about students in a psychology class took a final exam. As part of an experiment to see how much of the course content they remembered over time, they took equivalent forms of the exam in monthly intervals thereafter. Okay, so the average score for the group, F of T, average score for the class, okay, is given by 88 minus 15 times, what does ln mean? Natural log, when the base is The base is E. Excellent. Part A. Okay, I'm sorry. And T is the time in months between 0 months originally and 12 months a year later. What was the average score on the original exam? What am I asked to do and how do I get it? So part A, original score. How do I determine the original score? When we talk about original or initial, what do we really have in mind? We are thinking of time being how much? What is the age of or what is the original age, I should say, of a newborn? 0. So that's always original. Original, initial, means T equals 0 months. So I have to find F of 0. We'll put in the calculator in a minute. Part B. What was the average score after 2 months? And then 4, and then 6, and then 8, and then 10, and then a year later. What am I asked to do now? What am I asked to do? Exactly. 0, 2, 4, 6, 8, 10, and 12. Excellent. Of course, I'm not going to do this by hand. I'm going to enter the function in the graphing calculator in y equals as 88 minus 15 natural log of t plus 1. There is no t in the calculator. I have to use x. So I enter the function as 88 minus 15 natural log of x plus 1. And now I will go to second table. Of course, I have to make the correction here. So second table, and I plug in the numbers I need. 0, 2, 4, 6, 8, 10, and 12. So when time is 0, what was the average score? How much? Perfect. When time is 2 months, 72. When it's 4, it's 64. When it's 6, it's 59. When it's 8, it's 55. It's 10, 52, and then 50. What do you conclude? I don't know if they ask us in a minute. We'll continue reading the problem. But what do you conclude? That the average score initially was 88, and what happens over time? It decreases. Yes, I see that. I agree. Perfect. Part C. Sketch the graph, either by hand or with a graphing calculator. Describe what the graph indicates in terms of, we already answered that question. So I would like to present it first by hand and then with a graphing calculator. So remember, we're only looking at 0 to 12. So 2, 4, 6, 8, 10, 12. 2, 4, 6, 8, 10, 12. So that's time t. But as you see here, it starts at 88 and it drops to 50. So I'm going to say 2, 4, 6, 8, 10. So this is 100. It starts at 88. And then at 2 is 72. 2, 4, 6, 72. And so on and so forth. And 12 months later is at 50. This is what I expect the graph to look like. The reason why I wanted us to look at it first or draw it first by hand is to realize what kind of viewing window we need. So let's go to window. 0 to 14 is good enough with a scale of 2. Y minimum, I don't care for negative values, that's for sure. But let's put -4 just to see the x-axis. And to 100, so maybe we can see it. And then 20, scale of 20. So let's hit graph. And this is exactly what we expected. It's coming from 88, and it will drop over 12 months to 50. So this is the graph of f of t. Always please write the name 88 minus 15 natural log t plus 1. Any questions? Any questions on this? Any questions? Okay, in section 4.3, we will talk about properties of log. This function log is really special. The properties that this function has, there are 3, plus something additional. In a minute, I'll explain. So these 3 properties are typical to this function. You will never encounter another function that has these 3 properties. And we've never seen this before. This is totally new, unexpected in a way. So if we want to apply log in any base, or let's say base A, of a product of 2 different factors, then this is the same with the sum of the logs. So log of a product is the sum of logs. And I'll give an example in a moment. So this rule is called the product rule. Do not confuse this with log of A times log of B. That is not the same. They have nothing in common. So if you're thinking of something like log A times log B, this is not this property. This is log applied to a product. Here's an example. A log of 2x. Since I didn't write a base, what is the base? Perfect. So this is the same with log or common log or base 10, log 2 plus log x. Why? Only because these 2 were multiplied. So I could change the log of a product into the sum of logs. And this is the product rule. We'll have plenty of examples in a minute. Let me introduce 2 more properties to you, and then we'll work on problems. Any questions? We have never seen this before, right? Totally new. Here's another one. Log of x over y, or a over b. What do you think this will equal to? If the product changed into a sum, log applied to a ratio will change into? Exactly. Awesome. Well done. So log x minus log y. Of course, this is the quotient rule. Exactly. This is the quotient rule. Here's an example. Log, common log, of 2 over 3. How would you rewrite this? Exactly. Excellent. Well done. Good. Last property. And an extra thing that I already mentioned. Here's the last one. Log in any base of x raised to power b. So the first property was when we applied log to a product. The second one to a ratio. The third one is to a power. X raised to a power. Here's what happens. This piece, the power itself, goes in front as a factor. When we say a factor, it means it multiplies log. So this is b times log x. Very helpful and very good property to remember. Of course, this is the power rule. Here's an example. ln, what base is that? Perfect. Of x to the third. Can anyone give us an idea of how to simplify this? Exactly. Exactly. 3 ln x, meaning specifically not addition or subtraction, but multiplication. Exactly. 3 ln x. Okay, one more additional, I wouldn't call it a property, I would call it formula if you want. It's the change of base formula. Oops. Change of base formula. Let's talk about this so we understand what this means. Last time we practiced a little bit on, let's say, log base 3 of 9. And we said, this is an unknown, but I know that this is a log equation, and I can change it into an exponential equation. Can anyone refresh our memory how to change this into an exponential equation? Remember, we always start from the base, and we always go counterclockwise. Exactly, awesome. So what could that power be? Remember, this function is one-to-one. We cannot find two different numbers, right? We can only find one. No, 3 to the third is 27. So then this will be 2. Excellent. This is 2 indeed. Only 3 squared is 9. But here's my question next. This was not difficult, was it? 3 squared is 9. So 3 to what power is 9? It must be 2. But here's another one. Log base 5 of 7. What is this? I don't know, but I can change it into an exponential equation. Can anyone try? Please try. Whatever equals 7. Well, I will never be able to tell you what the number is. I can tell you it's definitely between 1 and 2, because 5 to the first power is 5, and 5 to the second power is 25. So in order to get 7, it's somewhere between 1 and 2, closer to 1 than closer to 2. But I have no idea what it is. Can I determine it? Yes. Here's how. I change the base. From this base that doesn't make sense, it makes sense, but only if I can figure it out easily, into something I have in the calculator. So I want to find log base 5 of 7. So then I have two possibilities. Both will give us the same answer. One possibility is common log of 7 over common log of 5. Do not confuse this to this. This is log applied to a ratio, which is a difference of logs. What I'm showing here is totally different. So this is the quotient of two logs. The other option is ln 7 over ln 5. Again, this is a ratio of two logs. This is not log applied to a ratio. Both ratios have to give us the same answer, because there is, I hope you will agree, there is only one number that I raise 5 to get 7. It cannot be 1.2 and 1.9. It has to be just one number. So regardless of which one we use, but you cannot swap them. You cannot say natural log 7 over log 5. No, you have to be consistent. Base 10 of the number and then of the previous base, or base e of the number over the natural log of the previous base, one or the other. So let's do this with the calculator. So log 7 divided by log 5, or natural log 7 divided by natural log 5. Now, how do I check my answer? Let's say I don't believe it, although this is what I was expecting. I was expecting that it's a number between 1 and 2, definitely closer to 1, because 5 squared is 25, is way past 7. So how do I check the answer? Here's how I check the answer. I raise 5 to whatever I found, And if the answer is, then it's the correct answer. So don't erase what you have. Let me show you how we should do this. 5 caret, in parentheses, the previous answer. The previous answer, it recalls the whole thing. The previous answer is with the second key an answer, which is the negative symbol. And when you click enter, what should you get?
7.
Exactly. Thank you. Here's another way. You can say 5 caret, and you truncate this number to, let's say, 1.209. But will you get exactly 7? Very close.
How do we get answer again?
Second and answer.
And then what is the answer?
It's the
Negative symbol. The negative symbol. It says A and S on top of it. Did you find it?
Oh,
So if I truncate the number and I don't make the calculator to recall the previous answer entirely, then I still check, right? I can still check, but I'm not getting exactly 7. I can't get exactly 7. I either get a little bit more or a little bit less. Perfect. So now let's practice.
won't we round, like if once we round the number 6.9, it becomes 7 anyway, right?
Right, but that you cannot be certain that your answer is 100% accurate. But if you use the previous answer, then the calculator is using the whole calculation from before without truncating the number, without leaving anything behind. But yes, you can assume that, but it may be 100% or not. Is that clear? Good. Other questions so far? Okay, so let's use those properties of. Notice one thing. I did not show anything like this. There is nothing that you can simplify this into. I did not show anything like this. There is nothing that you can simplify this. In other words, log applied to a sum or a difference cannot be simplified. Only log applied to 3 quantities: product, quotient, or power. If you have a sum or a difference, you are stuck. You can't simplify that in any way, shape, or form. So on page 501, we would like to use these properties, the 3 properties that we looked at: product, quotient, and ratio, and power. Product, quotient, and power. And either expand or condense log expressions. We either expand or condense log expressions. So what does expanding mean? So here's an example for expand. On page 501, I let you choose if you'd like 1 through 40. If you want, if not, I will. 1 through 40. All of them are asking us to expand. I'm going to start with 28 till you choose. You can choose the next one anytime. Log base b of x cubed y over z squared.
Oh my goodness, so confusing.
So what are we trying to do? We're trying to apply the 3 properties we have and expand this to very simple logs. So if you remember, we had a very simple example a minute ago, like log 2 over 3, and you said this is log 2 minus log 3. This cannot be furthermore expanded. This is it. This is the simplest possible logs that we can have. In the same way, we're going to apply those properties here. So the first property I have to apply is for the ratio, like we did here. So this is log base b of x cubed y and minus log base b of z squared. So we finished with the quotient rule. Now I'm looking at the 2 logs we have, and I realize that one of them is a product, in other words, log applied to a product, and the other one is applied to a power. Well, I remember that log applied to a product is log base b of x cubed plus log base b of y. And I remember that when I apply log to a power, all I have to do is put the power in front as a factor, multiplies log base b of z. And we have one more step. This is a simple log. The next one is a simple log. Just the first one needs more attention. Just one more step. Because now there is a log applied to a power. So then 3 comes in front like it did here. So this is 3 log base b of x plus log base b of y minus 2 log base b of z. It's a lot of writing, but it's really nothing. So we applied first property one more time. We're going to have more examples in a minute. So we applied the quotient, log of the top minus log of the bottom. You came up with that idea. I didn't even say anything, right? You told me the property. And then this is a product. So the log applied to a product is the sum of logs. Log applied to a power, the power goes in front. And that was it. So this is a situation in which we were expanding. And if you're asking, okay, what am I trying to do here? Why do I need to expand? It's because when we expand, sometimes we simplify the logs. Now, you can also say, fine, expanding, but I kind of understand. But why would you ever want to condense? In a minute, we will see. If we don't know how to condense, we will not be able to solve log equations. So that's why we have to go backwards and condense. Okay, I'm ready for any problem you would like to see from 1 through 40 on page 501. If not, I will choose.
We need 26.
26 it is. Excellent. Very good. In 26, we have log, and it says the base is 8, 64, divided by the square root of x plus 1. Very good. Again, I start with a quotient. What would you tell me to write?
The log of 8, 64 minus
Exactly.
log of 8 square root of x.
That's it. That's it. That's the first step. Awesome. Perfect. Now, I'm asking myself, can I simplify log base 8 of 64?
Yes.
Very good. So always remember, 8, imagine the other side. 8 raised to which power is 64? 2. So this whole thing is 2. Well done. Great job. 2 minus. Now I have to think in terms of the square root. What is the power for the square root? It's 1/2. Power 1/2. So minus 1/2 log base 8 of x plus 1. And this is it. No one can further simplify this or expand it. Remember, there is no log of a sum. Do not get into the trap of trying to simplify this.
So why does the 1/2?
The power is the square root. The square root is power 1/2.
Okay, so to get rid of the
Square root.
radical.
Yes, because we have 3 properties and we have to exhaust them. If any of the properties is applicable, I'm not done. And here it's still applicable. And the property is the power rule. Can we go back to condensing, or you still would like to pick a problem from expanding? I'm more than happy to do any problem you want.